Hi, I'd like to talk about Newton's second law much closer to the way that Newton himself framed it in his investigations of collisions. Now, from the context of momentum, Newton said that a net force changes a quantity of motion, and his quantity of motion is the momentum, which we said was the mass times the velocity. So the derivative of momentum with respect to time would be equal to the net force, which could be a function of time. So let's multiply both sides by our differential element of time. So that means that our change in momentum would be our net force times our change in time. And if I integrate both sides from the initial point to the final point, I would just have my final momentum minus my initial momentum. And then on the other side, I would have the integral from my initial time to my final time of my net force with respect to time, integrated with respect to time. And this piece that we have on the right, we define to be called the impulse. And the symbol we use for impulse in physics is a capital I with a little harpoon over top. Because impulse, like momentum, is a vector. And this restatement of Newton's second law is known as the Impulse-Momentum Theory, which on the simplest level states impulse equals the change in momentum. So again, physicists can be bad at naming things sometimes, or very pragmatic, depending on your perspective. But there are a few other sort of ways that we can make use of this idea. So one of those is in thinking about expressing forces that might have complicated dependence with respect to time. So if you were to take slow motion video of, say, a baseball striking a baseball bat, you would see the baseball compress and expand, you would see the bat compress and expand, and if you were to build a force sensor into that bat, you would see a fairly complicated force structure. But if you could actually map out that force as a function of time, because it would be a well-defined force, then you could calculate the area under the curve, the integral, and that would allow you to express an average force based on that area compared to the total change in time where that force is acting. And we're actually going to make use of the fact that we can, with impulse, think about having average forces where there's a huge temporary spike to our advantage as we start talking about collisions. Now, the other thing that I really want to point out about this is a vector equation. Momentum has direction. Impulse has direction. If you want to change the momentum in the x direction, you need impulse in the x direction. And because time is a scalar, that means you need force in the x direction. If you want to change momentum in the y direction, you need impulse and force in the y direction. Same thing goes with z. And this idea is an incredibly powerful way of thinking about things. This is the equation of safety. This is the equation of rocket science. It's all tied into this framing of how force changes momentum. So for safety, say we want to stop an object. Stopping an object just means we need to take away the momentum. Well, how we take away the momentum depends on whether or not something's safe. I could have a large force for a short amount of time, or a small force for a long amount of time. So the world record for surviving a fall without a parachute is held by Vesna Vojevic, who was a flight attendant on a flight that exploded above the Alps, and she fell a distance of about 10,000 meters, ended up in a coma for 6 months, was in the hospital for a couple of years, but eventually made a recovery. Well, what saved her was the fact that it was an incredibly snowy winter, so as she fell through the snow, the compacting of the snow increased the amount of stopping time, which decreased the amount of force. It was bad. Like I said, there was a lot of blunt force trauma. She was in a coma, but she survived because of that. Stunt performers use the same thing. The giant airbags they jump into increase the stopping time, decreasing the stopping force. Similarly, since I talked about baseball a little bit ago, sometimes people say it's like, oh, you can hear the speed of an object. So if a ball hits a catcher's mitt and you hear like a clear slap, it must have been going fast. Well, having a lot of momentum to take away can increase the force, but also decreasing the stopping time increases the force. So if you stop something really quickly, well, the quicker you stop it, the more force there's going to be, and the more that collision is going to end up stinging your hand. So it's not necessarily always on the momentum side. We can always take a look too at the impulse side for investigating how to make things safer. Thanks for watching.